This video is brought to you by mywayteaching.com.
In this part, we are going to study about kinetic interpretation of temperature. See, we already studied the equation, and we can write that equation. That is, we studied the equation that is pressure is equal to 1 by 3 n m mean square speed, isn't it? And we can write this equation as PV is equal to 1 by 3 n v m v bar square, isn't it? That is PV is equal to 2 by 3 n x raised x 1 by 2 m v bar square, isn't it? Here capital N is equal to n into v is the number of molecules in the sample. The quantity in the bracket, that is this one, it is the average translational kinetic energy of the, that is 2 by 3. In this one is the average translational kinetic energy of the molecules in the gas. Since the internal energy E of an ideal gas is purely kinetic, we can represent it, that internal energy of an ideal gas. That is given by E is equal to n 1 by 2 m v bar square. Then we can write the you just compare this with the equation that we just studied before, and we get PV is equal to 2 by 3 into E, isn't it? So we are now ready for a kinetic interpretation of temperature. Combining this equation with the ideal gas equation, that is ideal gas equation is the one that we studied before. That ideal gas equation is nothing but PV is equal to mu RT. So let us combine these equations and we can write E by N is equal to, or in other words, we'll write it in a simple way. E is equal to 3 by 2 kb nt, or we can write E by N is equal to 1 by 2 mv bar square, that is equal to 3 by 2 kb into T. That is, the average kinetic energy of a molecule is proportional to the absolute temperature of the gas, and it is independent of pressure, volume, or nature of the ideal gas. Okay, this is the fundamental result relating temperature, that is a macroscopic measurable parameter of a gas. Temperature is a macroscopic measurable parameter of a gas to a molecular quantity, namely the average kinetic energy of the molecule. The two domains are connected by the Boltzmann constant. So as you can know in equation, that is E is equal to this one 3 by 2 kb nt. Here you can see that internal energy of an ideal gas, E, the internal energy of an ideal gas, it depends only on temperature, isn't it? Not on pressure, even not on volume. With this interpretation of temperature, kinetic theory of an ideal gas is completely consistent with the ideal gas equation, and the various gas laws are based on this only. Okay, so it depends only on the temperature. So the internal energy, it depends only on the temperature, not on the volume or even not on the pressure. For a mixture of non-reactive ideal gases, what happens? Okay, in that case, the total pressure gets contribution from each gas in the mixture, isn't it? So we studied about that summation of, that pressures is given by 1 by 3 N1 M1 V1 bar square plus N2 M2 V2 bar square, isn't it? And it goes on. In equilibrium, the average kinetic energy of the molecules is different of different gases will be equal. When the system is in equilibrium, then the average kinetic energy of the molecules of different gases will be equal. That is 1 by 2 m1 v1 bar square is equal to 1 by 2 m2 v2 bar square. This is when the it is in equilibrium, then average kinetic energy is of different gases will be equal. Okay, so we can write it as P is equal to N1 plus N2 into kBT, isn't it? So this is Dalton's law of partial pressures. Okay, and here from the equation that we studied, that is E by N is equal to 1 by mv square. So here we'll get an idea of the typical speed of molecules in a gas at a temperature, that is T is equal to 300 Kelvin. The mean square speed of a molecule in nitrogen gas is given by m n2 by na. So that is given by, we know the data, we get 4.65 into 10 raised to minus 26 kg. Okay. So the speed is of the order of speed of sound in air. At the same temperature, lighter molecules will be having greater RMS speed. So here that RMS speed is given by 516 meter per second. Okay. Now let us see one simple problem. The problem is a flask contains argon and chlorine in the ratio of 2 is to 1 by mass. The temperature of the mixture is 27 degrees Celsius. Obtain the ratio of average kinetic energy per molecule, root mean square speed, that is Vrms, of the molecules of the two gases. Here they have given atomic mass of argon is 39.9 mu and molecular mass of chlorine is 70.9 mu. So here they have given the ratio of argon and chlorine. The both are mixed and the temperature of that mixture is 27 degrees Celsius. So we should find the ratio of average kinetic energy as well as root mean square speed, that is Vrms. We should find that also. Okay, and they have given atomic and molecular mass of argon and chlorine respectively. Okay, let us find the solution for this question. So the important point to remember is that the average kinetic energy of any gas, it can be monoatomic like argon or a diatomic like chlorine, or it can be polyatomic even. That average kinetic energy is always equal to 3 by 2 kb into T. It depends only on temperature and it is independent of nature of the gas. Okay. So coming to the first part of the question, here we should find average kinetic energy per molecule, isn't it? See, since argon and chlorine both have the same temperature in the flask, the ratio of average kinetic energy of the two gases will be 1 is to 1. Okay. So now let us find the solution for the second part of the question. So here we should find root mean square speed of the molecules of the two gases. Okay. See, 1 by 2 m Vrms square is nothing but average kinetic energy per molecule, and we also know that this is always equal to 3 by 2 kb into T. Okay, here m is the mass of the molecule of a gas. So we can write it as V square RMS by of argon by RMS value of chlorine, that is given by mass of chlorine by mass of argon, or molecular mass of chlorine by molecular mass of argon. In the question they have given Molecular mass of chlorine as 70.9 mu and argon as 39.9. So that will be equal to 1.77. Here m denotes the molecular mass of the gas. Taking square root on both the side, we get V RMS of argon by V RMS of chlorine. Both will be equal to 1.33. Okay. So here the composition of the mixture by mass is quite irrelevant